Hi everyone, my name is Tianyi Zhou, and uh, our work that we're gonna present today is called Fast Heavy Inner Product Identification between Weights and Input in Neural Network Training. And this is a joint work with Lianke from UCSB and Saayan Mitra from Adobe Research and Zhao also from Adobe Research and Yuanyuan from University of Washington. And so this is an outline for my presentation today. I will first give you an introduction about the problem that we are solving in this paper, and then I will give you the methodology that we use, and then I will present our result. So first, let's see the definition of heavy inner product. So given two sets A and B, which are both d-dimensional and they both have size n, and which are all independently and uniformly random except for the k vector pairs. So there are k vector pairs like small a1, small b1 to small ak to small bk. That's sampled from set A and set B, so that the inner product of them is larger than rho times d for some rho that range from 0 to 1. And the goal of the problem is to find these k correlated pairs. So this is a figure that help you understand the problem here. So for each subfigure, we generate two sets A and B, which are both 60-dimensional with size n, and where C pairs of them are correlated and others are randomized. The values of C and N are defined in the subfigures. For each entry in the correlated vector pairs, they have 96% chance to be the same and 4% chance to be different. For uncorrelated vector, we randomize all of them, and we randomly pick a pair A and B and calculate the dot product of them. We repeat this process 1,000,000 times and get this histogram. We can clearly see that the inner product of the uncorrelated pairs are distributed around 0, and their absolute value almost don't exceed 50, and which is smaller than the dimension of the vector. And additionally, the inner product of the correlated vector, which is the orange one, are distributed around 50. And our goal of the problem is to find these orange vectors. So in our method, we first set a high probability threshold for uncorrelated inner product, and then we partition set A and set B into n to the power of 2 over 3 groups. And so for each after partition them, there's like many groups of them, and for each group here we have there's a score function which we define as C, and then we accelerate the computation of that score function C. Now let's delve into the probability analysis for uncorrelated pairs. So for each pair X and Y in the product set, where X and Y are uncorrelated, the absolute value of their inner product is less than our threshold V, and this holds with probability of at least 1 minus 1 over n to the power 13, and this is a significant probability indicating a strong likelihood that uncorrelated pairs will fall below our threshold. And when we apply a union bond over all these possible pairs, which are in order of n squared, we find that the probability that the absolute value of their inner product is less than V for all such uncorrelated pair X and Y is at least 1 minus 1 over n to the power of 11. And finally, we identify the correlated pair denoted as tilted X in set A and tilted Y in set B, and these pairs satisfy the condition that the inner product of them is equal or larger than rho times d, which is equal to our threshold v. And in our analysis, we begin by partitioning set A and set B into n to the power of 2 over 3 groups. And so each group contains n to the power of n 1 over 3 elements. And for each element belong to A, we assign a random value ax, which belong to -1 and 1, chosen independently and uniformly. And let's consider a constant tau, which is greater than 0 here. And we define r as log of tau times n to the power of 1 over 3 based on omega for tau greater than 0. And then we define a polynomial function p as the following. So this polynomial will play a key role in our scoring mechanism. So for each pair of group I and j, we compute a score Cij defined by the following. So Cij expected value is 0 if pairs are not correlated, and for a sufficiently large constant tau, by applying the inequality, we can assert that the absolute value of it is equal or less than this value here, and with a probability of at least 3 over 4. And for this value, we denote it as theta. So if we repeat the process of selecting the ax value for each x independently and randomly log n times, the top k group pairs ai and bj with the score function greater or equal than 2 theta most frequently will likely contain the heavy inner product vector pairs. So once we identify the group pairs containing these heavy inner product pairs, it becomes a matter of a brute force search between k pairs of groups, each containing n to the power of 1 over 3 vectors, to output the final result. So given T is a summation of D choose I, where I range from 0 to R, let M enumerate all distinct subset of D of size at most R. We can reorganize the score function C as the following. So for some CS that can be computed in poly R time, where xm is defined as the product of the xi where I is sample from M. So then we define the matrix U and V by these two functions here. So we can see that the matrix products of this U and V matrix here is exactly the matrix of the value C that we desire to compute. So instead of computing the pairwise C function, pairwise C here, we can just compute the matrix U and V like once, and then we got the score function C. So the time complexity of computing this matrix multiplication is n to the power of 2 omega over 3 plus small o1. And additionally, we further speed up the calculation of matrices U and V as the following. So we let n be an enumeration of all subset of D of size at most R divided by 2. So for each I, define the two matrices here. So L and tilde L. So they are defined as this way. And compute the product of Pi and each desired entry U can be found as an entry of computed matrix P. So computing the entries of L matrices, naively take n to the power of 4 over 3 plus small o1 time. And computing the P, the matrix P here, takes time n to the power of 2 plus omega over 3 plus small o1. So all these computations are bounded by this time complexity here. So here it comes to our result. So for the heavy inner product identification problem that we defined earlier, there's a constant C 0 which is greater than 0, such that for correlation rho we can find the heavy K pairs in randomized time. The time here is the n to the power of 2 omega over 3 plus small o1. So when d is less or equal than c0 log n, which probably as 1 minus 1 over n to the power of 10 minus k squared divided by n to the power of 2 over 3. So with the probability at least this value, we can find the all the k correlated pairs. So next, I'm gonna introduce how our work can be applied to neural network training. So neural network training typically involves both forward and backward propagation, relying heavily on inputs, network weights, and activation function. However, in practical scenario, not all neurons are activated. So this brings us to the use of shifted ReLU function for improved efficiency in training. And the shifted ReLU function is defined as the following. So it's sigma x, which is the maximum between the inner product of WR and X and the BR. So the W is the weight here, and the B is just threshold. So this function, the definition of so the shifted ReLU function here is useful in speeding up the training process. So when we consider a two-layer fully connected neural network with M hidden neurons, utilizing this shifted ReLU activation, so the network function is described as the following. So this is a two-layer neural network, and the sigma here is just the shifted ReLU function. So one of the main challenges in training this network efficiently lies in the time complexity involved in computation. So for each input vector x, we need to compute m inner products in d dimensions. So this computational requirement leads to a natural barrier of m and d times per training iteration. However, when neurons are sparsely activated, conducting a naive linear scan to identify which neuron surpass the activation threshold become inefficient. So, and then our proposed method aims to efficiently locate the heavy inner product pair that activate neurons. This is especially relevant in settings where ReLU activation is used. So by implementing this method, we could speed up the neural network training process. And this is all for my presentation today. And this is the contact information. Thanks for listening.